Um, we're ready to we're ready to start. So hopefully everyone who wanted to attend is in the room. So a little background about me. I'm Christian Kosse. I've been at the Sports Center for many years, 5 years, and so now I'm at CUSP. So I went to industry, but I'm still associated. I still know all the folks at Sports Center and still maintain the software, more or less. And so I've been invited to this workshop to talk about BCILAB. And so I'm going to give a brief teaser. There's actually a track B, which covers that and other fancy state-of-the-art tools. And so later at 2, you can hop in and experience the rest of that. So this here is really just a quick overview and teaser. So BCILAB is a toolbox that ties into the EEGLAB ecosystem. And so it can be used to realize all sorts of BCI, brain-computer interface applications. So including both, clinical setups like spellers for disabled people, like the P300 speller that you see here, which is based on P300 EEG response, or assisted driving, for instance. Like this here was an experiment where the idea was to anticipate lane change intent using a brain-computer interface. So it's not just for clinical populations, but something that can also be used in the real world. And there are also gaming applications, of course. This actually turns out it's a video. So it's a Star Wars game, and your force powers are modulated based on how calm you are while you're wearing EEG. You see all sorts of brain products, equipment scattered in the room. So, and you can also use it for neuroscientific endeavors. So basically, you can use it to compute decoding models, which explain how certain cognitive variables, say attention, like in this case, can be decoded from brain activity. So in this case, it's a time frequency in different brain areas that explains the attention switch of a person between different modalities. So you can use it for that. You get very crisp models out of that. But it's interpretationally, it's quite different from traditional mass univariate and so on neuroscience data analysis. So these are some of the uses, and the toolbox that we build is a MATLAB toolbox. It's very much in the EEGLAB spirit. It has a nice user interface on top, and underneath there are a lot of methods in it. And in fact, the user community is sort of divided into two camps. One is method developers who develop and test new methods, new algorithms, like you see a whole list of them in this little grid here. And the other are people who basically just want to use some sort of off-the-shelf approach, and these would be the people who use graphical user interface and throw it at the data to like get started, or to get a feet wet in BCI, or to just basically like have some control over something, imagined movements or whatever it is. And so the bridge between these two worlds is the GUI. So it's built so that someone can go in and implement a state-of-the-art method, and someone else can pick it up and apply it to some new data, pretty much. Although it's, let's say, over the years it has become pretty clear that it's not exactly the most shallow learning curve. So people who want to go deep and basically really innovate, you basically have to read a lot of documentation to sort of dig your way in. But as long as you stay sort of shallow, it works pretty well. So the background is that this was developed for real-time cognitive state assessment. It was actually funded by the Army, it turns out, and so the focus was on advanced method development, rapid prototyping, and so on, evaluation of BCI. So it's not just methods, but it's also actually really testing and evaluation and offline and online analysis. It has, for a number of years, been the largest open source BCI toolbox when you count the methods and algorithms. Not sure if it still is. So now we at CUSP, we have new software. It's called NeuroPipe, which is in some sense on our end the successor. Well, it's the next generation, so to speak. And however, I think it's certainly still one of the largest. And so we build it basically with the EEGLAB ecosystem in mind. You know, it's open source, it has plugins, it's pretty extensible. And one thing I should mention here is the precursor to that was the Fupa toolbox, which Thorsten Zander and I developed back in Berlin in 2006, so more than 10 years ago actually. So you know, I'm always asked to put in that little note there at the bottom. So what I'm going to show you is a quick teaser of how this works, how one can use that toolbox. So say you have MATLAB, I've actually already loaded the toolbox. You get a little menu here where you can start working. And so suppose we start working with the GUI. The first thing, let's suppose we want to, by the way, I don't have any hardware with me. I'm going to show this basically pretty much on playback data. Suppose you want to predict whether a person is imagining left or right hand movement based on continuous EEG. So the first thing you do is pick an approach, that's this button here. And so you have a whole lot of options. These are pre-built paradigms that you can start from and customize. So for instance, you might use filter, bank, common spatial patterns. They also have some docs. Turns out the latest MATLAB version renders this in a somewhat funky way, but it will be fixed. So this is FBC speed. That's a pretty good method. And then you go ahead and you can customize some parameters. Suppose we want to use a 2 here instead of a 3. You can use different machine learning methods and so on. And then we say, okay, now I can save this on disk. For instance, I can generate some script code that I can use in a script later. And I can say, okay. So now we have our method. Now the next thing is, well, this method turns out to be machine learning powered. So it doesn't just run out of the box. You have to first have some calibration data, which is almost always the case in brain-computer interfacing. So you need to adapt to the person's specific brain patterns, etc. usually, and so you load some calibration recording, which you hopefully have already recorded. That is very much like a psychological type experiment where you present different kinds of examples of cognitive states, say left-hand movement, right-hand movement, imagination. So I'm loading some data set here, emag.set. That's a person imagining repeatedly left, right, and so on. And so now we can train our model. So that's all these buttons here, train new model. And the first thing that it asks about is, well, so which of all the markers in the data are the markers that tell us where the examples of left hand, right hand movement, imagination, and so on begin? Basically, these are called target markers. And you can inspect the data and then go through, and what we see here is, you know, there are basically only 2 kinds of markers, S1 and S2. 2 types of stimuli every 5 seconds. One stands for left hand, the other for right hand. Actually, the reason why this shows up here already is because I typed it in earlier when I tested. So it starts like this, and you kind of have to put it in. So these are the markers that I care about. There could have been others, we ignore them. And so now you can start computing. And there are a bunch of other options here that you can configure, like how it should evaluate how that method is likely going to work on future data, so you can revise and tune, and also where we want to save it in the workspace, but we're not going to change anything here. In fact, it's already crunching numbers. Should finish in a second or something, 2 seconds. So, and there's our result. So it actually gives us a little table here estimating what the likely error rate is. It says most likely error rate is 23% error, so 80 something, well, about 77% correct. And I could visualize the model now, for instance. Let's do that. So what this gives us is spatial patterns that correspond to different brain sources that this algorithm identified. So when you look in this row here, for different frequency bands, by the way, that's inherent to the method, there are a few good ones in there, a couple junk ones. These here correspond to sources in the motor cortex, which it found. That was pretty quick. And so let's say I trust that model that I computed, and now I can start running. So now I have to play something back. I can do that in another MATLAB. In fact, this 2-line script here loads some other data and plays it back. I already have it running. And so now I can choose where I want to read from. I can pick different kinds of devices. The most useful one is lab streaming layer, which is a technology that was developed at Swartz Center that allows you to read from any, basically 80% of the EEG devices out there, the bigger ones. And so, you know, you can pick what device you want to read from. I say any EEG device, whatever's there. There's only one, that's the playback. Now it's reading, and now I can, my model is there, I've computed it, right? So now I can use it and send the output somewhere. And I say, well, okay, I send it back to the network, LSL. You can configure a bunch of stuff. By the way, there are tooltips here that explain what these things do. There's also help when you click this button here. Should bring up some help. Takes a while for my browser to load. And so say I want to compute the probabilities for left hand and probability for right hand. And so now it's streaming. Now I can start an external application, say a game, which picks up these data. And so I start this one. Pretend that this is a fancy spaceship that's banking left and right. So this here is a very simple demo that just shows a bar that extends to the left, if you're imagining left hand, extends to the right. When you follow this a bit, you basically kind of see what the pacing of that session is. Basically about every 5 seconds the person is asked to imagine a different kind of movement. It's a little jittery. Sometimes it's unsure, it's sort of in the middle. And so there's your BCI. So that was pretty quick to start. Now what you could have done is maybe you would normally do a bit more R&D, right? So maybe you actually want to assess this offline instead of putting the subject under the cap, and then if it doesn't work you say sorry and gives them $15 or something. So basically you can load another data set, so let's call it last data 2. That's actually one we also played back. And now you can apply that model we still have in memory to that data set. Actually, I think I have to, yeah, so here we go. I can pick which model. I have only one, which data. I have 2 data sets. I pick this one. And so I apply that. And then I'm going to get some sort of offline assessment of how well that model works on these data. Should be pretty quick, actually. And then I can go ahead and tune it, right? So you may choose a different approach, you may alter the parameters, add more filters, remove artifacts, any of those things. And in fact, we're kind of getting, I think, close to the end of my slot, right? It takes under 140. Yep. So, you know, it turns out, you know, this is not the fastest laptop here. It takes a bit of time to load. But I guess you get the idea. This thing will spit out another table just like the one we just saw, and you know, basically give me the offline results for how well that, you know, that method is working on these data. And then I can visualize that. I can tweak some more parameters, and you'll get to see. Well, actually, it turns out we started late, right? So that's why I still have a bit of time. But honestly, I don't feel like waiting here. You know, maybe my laptop is a little overloaded. Yeah. So anyway, so you can also do batch analysis, which is this button here, where it shows you all the approaches you have built, and you can maybe remove one, like this one here, and all the data you've loaded, like these 2, and then you can basically run every approach on every data set. And so in fact, it crunched through really quickly this time, and gives me all the results, it writes them somewhere, and so this way you can be really systematic about it. And you can also script, so like here is something very similar in scripting form. There are some tutorial scripts that are included, like load the data, choose approach, train, compute results, and there are actually quite a lot of examples for how you customize the approach and so on and so on. And you can do that also in tandem with the GUI. You can basically look up in the GUI what the parameters are called and then type them in the script, of course. Yeah, so here we go. That was 18% error, a little better, plot it and so on. So that's our script running. All right, and so that's our quick demo. Again, there will be a track about that. So yeah, just hop in if you want to see it. Any questions? Very good. Everyone knows everything. All right. Okay, I hand off to the next little demo teaser. I think that's going to be Tim. Thank you.